Dear learners, the topic for discussion is simple harmonic motion. In order to sensitize about this topic, I would like to mention that this finds application in many areas of physics, science in general, and more importantly in our real life situations. Think of a very great musical performance. Now, that depends on simple harmonic motion. Processes like nuclear magnetic resonance, processes for determining the electronic transport properties in solids, all these are dependent on simple harmonic motion. Now, I will take you back to the 16th century in the year 1580 precisely, when Galileo was 16 years old. As you know, he was called the father of observational science. He was sent for studying medicine by his father, which he did quite reluctantly, but he has developed a good bit of knowledge of human anatomy. And during that period, once he was sitting in a church when there was a big storm, so much so that the chandelier started swinging, and he observed that the chandeliers which are longer are taking longer time for swinging, those which are shorter are taking shorter time for swinging. But more than that, what significant thing he observed was that the time period of oscillation, I will explain this term later, the time period of oscillation, that is the swing from one end to other and returning back to the original place, is independent of the angular spread of the chandelier, that is the angular spread of the swing, which is otherwise called angular amplitude. Now, if you would recall, Newton's Principia was published in 1687, that is 107 years later, and it took another 3 years or so to stabilize, that is about 110 years after this empirical observation by Galileo, this could also be established through Newton's laws of motion and further analysis based on that. But Galileo had observed it empirically more than 100 years ago. Now, please wonder that Galileo had measured the length and a lot of provision was there, but how did he measure time? Now, there was no particular device for measuring time, like I am wearing a wristwatch. There was no such device at that time. But whatever little knowledge of anatomy he has gathered, he could make out that our pulse beat is a periodic motion. It gives me shivers through my spines to just visualize the situation, the circumstances under which the ready wit of Galileo Galilei had walked, and he calibrated time using the pulse rate, and thereby he measured time and came out with such accurate observation which stood the test of time. And this inspired Christian Huygens, the person whom you know for his wave theory, to develop the first wall pendulum, which was a bar pendulum. And as you know, the clock which uses this bar pendulum can be used only when it is stationary. You cannot use it when it is mobile. So, there came instruments or devices like this, but this also has a quartz oscillator. The most sophisticated clock, the atomic clock, also has an oscillator. Now, what is oscillation? Oscillation is a periodic motion. Periodic motion means a motion which repeats itself, and we study all sorts of periodic motion by beginning with what we call simple harmonic motion. In today's lesson, we would be defining simple harmonic motion. We will apply mathematics, particularly trigonometry and little bit of calculus, to understand the phenomena of simple harmonic motion and to further understand the meaning of the different terms associated with it, like amplitude, frequency, phase, epoch, and so on and so forth. And then we will make an analysis about the overall transformation of energy that takes place during an oscillation, and finally, we will extend it to something called damped harmonic motion. Now, as I told you that simple harmonic motion happens to be the beginning of our study of any kind of periodic motion, a motion which has a definite period. So, an oscillator which is moving from one particular extreme to another and then getting back to the original position is said to have completed one oscillation. Now, if it does so time and again, and in every passage if the time taken for one complete oscillation is same, then the motion is harmonic, and the time it takes for completing one oscillation is called the time period, and the number of times it does that within unit time, that is within a second, is called its frequency. Very prolific examples of oscillators which we will be studying in your syllabus are the spring mass system, where you can see on your screen that the spring is made to oscillate by just pulling the mass, and then the most ideal example, the most illustrative example which you are seeing now on your screen, that is the simple pendulum, where you have suspended a heavy metallic bob with the help of a string from a stand. Ideally, a simple pendulum is a heavy point mass suspended from a rigid suspension by a weightless inextensible string. But none of them can happen in reality. You cannot have a rigid suspension. So, we approximate that by the kind of stand that is available in the laboratory. You cannot find a weightless string. So, we do it with the help of a thread, and which you can consider by and large to be inextensible also. And then at the end of the thread, we tie what we call a spherical bob, which approximates a point mass. So, now we will study simple harmonic motion using these devices. But as I told you that the motion is periodic, and then comes the application of mathematics. Now, among the different trigonometric functions which you have studied, you must have seen that cosine function and sine function, they follow a kind of a periodicity. They oscillate between the values +1 and -1. So, you are seeing the sine function on your screen. It is 0 for theta equal to 0, 1 for theta equal to pi by 2, again 0 at theta equal to pi, -1 at theta equal to 3 pi by 2, and again 0 at theta equal to 2 pi. So, we say by the passage of theta from 0 to twice pi, it completes a period. You might be asking that it attains the value 0 also at theta equal to pi, but why we do not say that it completes a period in pi? This is because at pi the value of sin theta is definitely equal to 0, but at that point it is in the decreasing mode, whereas at theta equal to 0 and theta equal to twice pi, these are in increasing modes. Same with the cosine function, it is 1 at theta equal to 0, 0 at theta equal to pi by 2, -1 at theta equal to pi, 0 again at theta equal to 3 pi by 2, and 1 again at theta equal to twice pi, the periodicity again being twice pi. And these sort of functions, which are either sine function or cosine function, are called sinusoidal function. And so, the most fundamental definition of simple harmonic motion is that a motion for which displacement versus time curve is sinusoidal. So, let us consider a linear simple harmonic motion, that is simple harmonic motion taking place along a straight line. Let this straight line be the x axis, and this point is x is equal to 0. Now, as I told you that the displacement time curve would be sinusoidal. So, the equation is written as x is equal to a sin omega t. So, we have to worry about a and omega. we wanted to relate x and t through a sinusoidal function, which has been done. But where from these two things come? They come absolutely from the consideration of dimensional analysis. See, if you go for the expansion of sine function, it is a power series, sin theta equal to theta minus theta cube by factorial 3 plus theta to the power of 5 by factorial 5 and so on. So, theta has to be essentially dimensionless, otherwise a havoc will get created. But t is not dimensionless. So, in order to make the argument of the sine function dimensionless, we multiply that with omega, which has the dimension of reciprocal of time. And then what happens to sin omega t? All the terms are dimensionless, and so had there been only sin omega t on the right hand side, all the terms on the right hand side would have been dimensionless, making it a completely dimensionless term. So, we multiply with a, which has the dimension of length, so that it matches the dimension of x. But now they assume special significance in the study of SHM. What is the significance? The maximum value of x is a, because maximum value of sin omega t is 1. So, this is called the amplitude of simple harmonic motion. In order to understand omega, we have to do a little bit of calculus. See, we have to consider the status of the position of the oscillator by simultaneous consideration of displacement as well as velocity, like we did in sine function, not only the value of sin theta, but whether it was increasing or decreasing. Velocity, as you know, is dx dt, and that works out to be a times omega cosine omega t. Now, the periodicity of both these functions is twice pi, as I explained little while earlier. X has to be periodically repeated, v, the velocity, also has to be repeated with the same period, and that happens after omega t is equal to twice pi. What I mean to say is that sin omega t is equal to sin omega t plus twice pi, cosine omega t is equal to cosine omega t plus twice pi. There may be other associated angles also, which may satisfy the sine equation, which may singly satisfy the cosine equation, but only with plus twice pi both gets satisfied. So, the period increases by twice pi, and therefore, we multiply omega by capital T, which we call the time period, and we say that omega times capital T equal to twice pi, where T is equal to twice pi by omega. This is the time period, or in other words, omega is equal to twice pi by t, and as I explained that the reciprocal of time period is frequency, which we generally denote by nu. So, omega is equal to twice pi nu. So, we have obtained the significance of A and omega. Omega is directly related with the frequency nu, and it is called the angular frequency. And then in both the expressions of displacement and velocity, omega t appears in the argument, and so that describes what we call the state of motion or the phase of vibration, and therefore, omega t is the measure of what we call the phase of SHM, and this would be extremely important in the study of wave motion. In general, phase is expressed as omega t plus delta, because the motion may not start from the origin at t equal to 0. It may start little departed from the origin, and that is why we have to accommodate another term delta, which is called the epoch of SHM, and the generalized expression for phase is omega t plus delta. So, we have understood the meaning of the constants a, omega, and we have introduced a new constant delta, and we have been able to relate it to the different features of SHM, that is amplitude, frequency, time period and phase. And a quick look at the expression for velocity. Velocity we have already derived equal to a omega cosine omega t. So, we will do a little bit of trigonometry. Cosine omega t is equal to square root of 1 minus sine square omega t, and that is equal to, if you recall the expression of sine omega t, that works out to be 1 minus x square by a square, and so this is 1 upon a root over of a square minus x square. So, velocity being equal to a omega, you will recall cos omega t. So, this is equal to omega into square root of a square minus x square. So, we have arrived at the expression of velocity, and a quick look at the expression for acceleration. V is equal to a omega cosine omega t, acceleration is equal to dv dt. So, that is equal to minus a omega square sine omega t, and a sine omega t is equal to x. So, f is equal to minus omega square x. From that you can also write the force based definition of simple harmonic motion. Force is equal to m into f, where m is the mass of the oscillator. So, that is equal to minus m omega square x. In other words, the force is proportional to displacement, but it is directed towards the mean position because of this negative sign. This negative sign is crucial. So, what happens that you have removed the oscillator from the mean position, but this restoring force is bringing it back to the mean position. The force is proportional to x, but that does not mean that it goes on increasing. Because of this minus sign, it is getting restored back to the mean position. So, we say that the definition is f is equal to minus kx, and this k is called the force constant. It is given by k is equal to m omega square, and from this you arrive at omega square is equal to k divided by m, omega is equal to square root of k divided by m, and t being twice pi divided by omega. So, t equal to twice pi root over of m by k. This is the expression for the time period of a simple harmonic oscillator. Now, had it been an angular oscillation, now the two examples which you had seen, the spring mass system, that is a linear SHM, whereas in the case of simple pendulum it is an angular motion basically. Let us forget about SHM. If we just look upon these examples as a linear motion or an angular motion, then the spring mass system presents an example of linear motion, whereas the simple pendulum presents an example of angular motion. So, in that case also we would be arriving at similar results, but mind you, in the case of angular motion it is not the force, it is torque, and what would appear as the constancy is called the torque constant. Like there it was f is equal to minus kx, here it would be torque is equal to minus torque constant into theta. that is the angular displacement. So, this result would get replaced by T is equal to twice pi in place of m, you would remember it would be replaced by the moment of inertia, and k would be replaced by K A, which is the torque constant, not the force constant. Now, what happens in the case of the simple pendulum? So, this you can take directly to be the expression of time period for the spring mass system, and in that case k at times is called the spring constant. The force constant is also called the spring constant, because it happens exactly in the case of a spring, that is due to the stretching of the spring there is restoration due to the elasticity of the spring, and the restoring force is exactly equal to k into x. Whereas, what happens in the case of simple pendulum requires little bit of knowledge of angular motion, that is, this is the mean position of the simple pendulum and it is oscillating along a circular arc like this. We are observing it when it is at an angle theta. This is the bob whose mass is equal to m. So, the downward force is equal to mg. It has two components, one along this direction, another along this direction. This component is m into g into cosine theta, which basically goes to balance the tension, let me call it T0, the tension, and of course, the value of tension, which is a self adjustive force, gets adjusted in accordance with the angle theta in mg cos theta plus the centrifugal force, and this component is mg sin theta, which produces not the restoring force, but the restoring torque, and this is the axis of rotation. So, about this axis the torque will be equal to mg sin theta times the length of the thread, which is L. So, the restoring torque is equal to mg sin theta into L, and I put that minus sign because it is a restoring torque, because theta is increasing in this sense, whereas the restoration takes place in the opposite sense, hence this minus sign. Now, simple harmonic motion is an approximation, and this happens when theta is very small. So, that sin theta can be replaced by theta, and so we write this as minus mgl into theta, and the torque constant is now equal to m into g into L, and so the time period is equal to 2 pi root over of I by the torque constant, and you are very much aware that I in this case is the moment of inertia of the point mass, which is at a length L from the axis. So, that is m L square, and the torque constant, as you have seen, is mg L. So, you get the good old result T is equal to 2 pi root over of L by G. So, that is how we arrive at the result for the time period of oscillation of the simple pendulum. So, a little bit of discussion about the energy consideration. Now, let us study the simple pendulum. When you have taken it into one extreme, it has maximum potential energy, zero kinetic energy. Any system in this universe has a tendency to minimize its potential energy, and so it would come down to the mean position. But it cannot stop there, because it has gained maximum kinetic energy there. So, it has a velocity, it has an inertia, and so it overshoots that position and again goes to the other extreme where it has maximum potential energy, which it has again got to reduce. So, it would come back and retrace the path, and thus the energy alternates between potential and kinetic form, and the system goes on oscillating. So, that is the feature, energy alternating between potential and kinetic form, and if it is an ideal conservative system, then the kinetic plus potential energy is equal to a constant. I leave it as an exercise for you to work out the expression for kinetic energy and make a plot of kinetic energy versus x from x is equal to minus a to x is equal to plus a. Do it similarly for the expression of potential energy and draw the graph of potential energy from x is equal to minus a and x is equal to plus a, and then make a plot of kinetic plus potential energy and convince yourself that the sum total is constant and that the graph is a straight line parallel to the x axis. Now, if the system is not conservative, as it happens in the real life situation, then the total energy does not remain conserved and energy gets dissipated, and so something happens with this oscillation which is called damping, and this we will see through this demonstration. So, for the demonstration purpose, we have set up a simple pendulum into oscillation, which you can see on the screen. Now, this is not an ideal simple pendulum from the point of view of the fact that it is not oscillating in vacuum. We have the usual air around it, and which provides a good amount of resistance which we call air resistance. So, this is a kind of a dissipative force to which I was making a reference, and due to this dissipative force, the total energy does not remain conserved. In fact, during this oscillation, as I told you, that energy alternates between kinetic and potential form, and kinetic plus potential energy remains constant, but that happens in the ideal situation. It does not happen here. The extent of oscillation reduces once it is kept like that for a longer time, and we say that the oscillation gets damped. So, this is called damped harmonic oscillation. So, with this I think we can summarize all that we have learnt. We have studied simple harmonic motion, we have defined simple harmonic motion, and we have written the equation of simple harmonic motion from a very rudimentary consideration. We have used the constants which appear in the equation of a simple harmonic motion and have related it to the three essential features of simple harmonic oscillation, that is amplitude, time period and phase. And then we have given you the measures of time period. We have related that with angular frequency, and we have obtained a measure of phase. And finally, we have given a demonstration of damped harmonic oscillation. There are several other factors. Of course, here we have given you the main features of the chapter on simple harmonic motion. Please read it very thoroughly, very carefully, and you should brush up your ideas, your concepts of trigonometry and little bit of calculus before you go through this chapter. I hope you will enjoy learning simple harmonic motion, which finds application in several situations in physics, particularly when you will be learning wave motion. So, I wish you all the very best. Thank you.